Welcome to our channel, where we explore the fascinating history behind the inventions that changed our world. Today, we're doing a deep dive into one of the most brilliant yet ultimately flawed pieces of wartime technology.
The Enigma machine.
Exactly. We're going to explore how this drive to automate encryption completely changed warfare, and how a couple of, well, simple errors brought the whole system down.
You really have to start with the context of World War II. The Axis powers were, frankly, outnumbered.
Right.
So their entire strategy depended on surprise, widespread surprise attacks. And for that, you need communication that is instant, but also completely secure.
So the goal was basically to create a machine that could automate the perfect code, the one-time pad.
That's the gold standard.
Okay.
A one-time pad applies a truly random shift to every single letter. The dream was to build a machine that could generate a sequence of shifts so long and so complex, it was for all intents and purposes random.
Okay, let's unpack that, because that's the core problem, isn't it? How can a machine be random? Machines are predictable by design.
They are. I mean, any machine starts in a set state. You give it an input, it performs an operation, and you get a repeatable output. Always.
So the trick was to make that repeatable cycle incredibly, incredibly long.
Hundreds of years long, ideally. And that's where the idea of the rotor machine comes in.
The state-of-the-art tech at the time, I think the easiest way to picture it is like an odometer in a car.
It's a great analogy. It's a mechanical process that just ticks forward, and it takes, thousands and thousands of miles to get back to all zeros.
Now, just imagine scrambling the numbers on those odometer reels.
Exactly. So as it ticks forward, it's not just adding one, it's generating a totally new electrical path through those scrambled rotors.
So every time you press a key for a message, say for attack, the rotors click forward one step.
And the machine's entire internal state changes. So the first A in attack might become X, but the second A will become something totally different.
And the complexity just explodes from there, with 3 rotors, each with 26 positions.
You're looking at 26 times 26 times 26.
Which is 17,576. That's a huge sequence of unique shifts.
It's a massive list. And your security depends on you and your partner starting at the exact same point in that sequence.
And this is what the Germans adopted with the Enigma machine.
Yes, it was an electromechanical masterpiece. Each rotor was this disk with a maze of wires inside. So when you pressed a key, the current went on this wild journey from an input letter, say A, to an output letter, maybe Q.
And when the rotor advanced, their whole A to Q path shifted.
A whole new substitution cipher every single time. And this is where we get into the idea of a key space.
The key space being all the possible ways you can set the machine up at the start.
Exactly. And the Germans didn't just have 3 rotors. They could choose which 3 to use and what order to put them in.
So the key isn't just the starting position, it's which rotors you're using and in what order.
Right, which takes that 17,000 number and multiplies it again. If you can arrange 3 rotors in 6 different ways, your key space suddenly jumps to over 100,000 settings.
And they kept making it more secure, adding more rotors.
They added a 4th rotor. They increased the pool of rotors operators could choose from.
Which brought the total number of possible setups to, get this, over 150 million ways.
Just a staggering number. And it gave the German high command total confidence. They figured even if the Allies captured an Enigma machine,
they could never check all those settings in time. It'd be like guessing the outcome of 26 dice rolls all at once.
They thought their communication was completely unbreakable.
But that huge complexity was hiding two fatal flaws, one human and one baked right into the design.
This is where it all starts to unravel. To communicate, 2 operators needed to set their machines up identically using a daily key sheet.
So the sheet tells you which rotors to use that day, what order to put them in, all the big stuff.
Right. But then for each individual message, the operator had to do one more thing. They had to pick a random starting position for the rotors.
And this is flaw number 1, the procedural error.
It's just human nature. The instructions said to make it random, like roll dice. But if you're a tired operator under pressure,
you're not going to roll dice. You'll just click the wheels a few times. Or you'll use something easy to remember, like AAA or your girlfriend's initials.
And that one shortcut destroyed the randomness. Instead of starting points being spread evenly across all 17,576 positions,
they were clustered in a few dozen lazy, predictable spots.
And that was the opening. The code breakers of Bletchley Park could analyze hundreds of these messages and see the patterns. It allowed them to work backward and, after a huge amount of effort, figure out the fixed wiring inside the rotors themselves.
That's incredible. They reverse engineered the hardware just by analyzing human laziness.
But even with the wiring known, they still needed a way to find the daily key from that giant pool of settings. And that brings us to flaw number 2, the design error.
Yeah, this one is fascinating. The Enigma was designed so a letter could never encrypt to itself.
The designers thought it was a strength,
Yeah.
a security feature. If you typed the letter L, the lamp that lit up could be anything except L.
Why? What was the thinking there?
They figured it would add more confusion, but for a code breaker, it does the opposite. It gives you a huge piece of information.
It tells you what the letter isn't.
Exactly. It reduces the possibilities. And that constraint is what made their code-breaking machine, the bomb, possible.
The bomb. This was initially a Polish design, then massively improved by the British and Americans. How did it use that flaw?
The bomb worked with cribs. A crib is just a piece of text you're pretty sure is in the original message.
Like a weather report or Heil Hitler, something predictable.
Right. So you'd feed the encrypted message and your suspected crib into the bomb. The machine would then rapidly test key settings. And because of that no self-encryption rule, if any setting resulted in, say, the E in weather encrypting to an E,
It would know that setting was impossible and would just throw it out immediately.
instantly, it filtered out millions of wrong answers in seconds, leaving just a handful of possibilities to check by hand.
And the result was that the Allies could find the daily key in just a few hours.
Sometimes minutes. They were reading German commands almost as fast as they were being sent. It was a fatal blow to a strategy based on surprise.
So it all comes down to this. You have a machine with near infinite complexity, but it was defeated because human and design flaws drastically shrank the searchable space.
It's the key lesson. Complexity is not security. If those operators had just rolled dice for their starting positions, the wiring would have remained a secret.
And if the machine had just allowed a letter to encrypt to itself, the bomb couldn't have used cribs effectively. The Allies would have been stuck searching that impossible 150 million space.
It's a powerful lesson. The technology was brilliant, but the procedures for using it and one tiny design choice created the opening.
And you have to wonder, the outcome of World War II could have been so different if not for those two errors. One human, one technical. It's a lesson that still holds up today in everything from military security to just, choosing a good password. Thank you for watching. If you enjoyed this video, don't forget to subscribe, like, and let us know in the comments which invention you'd like to explore next.